Thank you very much, everyone, for those kind words. All back to you. Really being proud that I'm part of this movement, part of this great group of people, and have been for the last decade or more now. How time flies. Only having fun with PH, of course. And it's not going to be funky tonight. I'm going to put a different spin on it and try to keep all the technical stuff a little bit light. I know it's a little bit later for some of you in the Eastern time zones, so I don't want to bore you too much with technical details. But as you know me, the ones you know me, I could talk forever and get into the depths of those. So I'm definitely open to take it further if you have some more questions. I'll start my slides here now. Hope you can all see that.
Looks great.
So today, yeah, good. Today I'm going to tell you a fairy tale of the perfectly insulated building. And it starts once upon a time in the great white north, where most of us live. And there lived a princess called GAIA as well. Princess GAIA was always cold because her castle had no insulation, a terrible form factor, lots of thermal bridges, and an ACH of 50, only single pane windows, and no HRV. Her father, old King Cole, was at the end of his resources. And after a lot of thinking and consulting with his court, he made the announcement. Whoever could form a plan to provide thermal comfort for his Princess GAIA would have her hand in marriage. Suitors came from far and wide, among them Sir Heat-a-Lot from the country of unlimited resources, Herzog von Greenwash from the country of hypocrisy. But none of them were good enough for our Princess GAIA. She had almost given up hope when along came a young squire from the house of Passif, only armed with his wits and good intentions. And he presented her with his plan. 5 basic principles will guarantee thermal comfort as well as high level of energy efficiency. And as most of us know, there's thermal insulation at high levels, passive house windows that are high performance, orientated properly, using ventilation with heat recovery, getting high level of air tightness, and also try to avoid thermal bridging in design and construction. There could be a 6th that we could add, and that has to do with the form, the design of our buildings, how compact they are. But typically we talk about the 5. And today's focus is on the first principle, the super insulation. Very important for those who are new to the standard to realize the key element that it is a performance-based standard. So that means there is no prescriptive path, really. There is no rule of how much insulation do we need to put in our assemblies. A passive house in Vancouver looks different than a passive house in New York. And Princess GAIA asked, but where do we start and how do we figure out how much insulation we need for our projects? Well, you can start with a model, and that just goes hand in hand with our design. Definitely at a stage where we have schematic design ideas, volumetric ideas of our buildings. I highly recommend using Design PH. It's a very easy to learn tool. It's a plugin to SketchUp. Anyone can learn SketchUp in a few hours to draw enough that you can use it to start modeling your design project at an early stage. But it goes further. You can run different scenarios. So you see a little bit in the background here, a lot of the, this is from a project I've worked on. I started out with the baseline. So this particular project, they came to me and they already was designed, not as a passive house, but they asked me, can we make this a passive house? And I said, yeah, I'll try and I'll model it and see what we can do. So started out with a baseline, and I think it was around 70 kilowatt hours of heating demand. And just by changing the quality of the windows, that already dropped down to around 30. And then start looking at the assemblies and the U values of those. So definitely one of the first kick at the can when you're looking at a passive house building and figuring out how much do we need, how much insulation do we need, what do we need to look at in terms of U values. Another approach would be to look for projects in your climatic region and get a basic idea of the adequate U values. There is an international passive house database, I'm sure you're familiar with, passivehouse.com will lead you there. Look for your region, look what has been done. I know Passive House Canada has their own one. I'm not sure what's happening in the US in that regards, but take advantage of your colleagues in your areas, even if you walk around and see someone is building a passive house, ask them what they're doing. And, you know, we're all sharing our lessons learned. And, you know, the Passive House Accelerator is the perfect example for that we can learn from each other the most. And remember that size and form do matter. And especially, you know, for smaller buildings, I would say they don't even have to have, you know, a very intricate envelope that has a lot of chalks and makes it bigger. It really depends also just on how many stories you have. I was looking at a passive house in Ottawa. That was a one-story rancher with a courtyard in it. And I had to tell the client, unless you're adding another floor or a basement, it's not very feasible to get to the certification. So for us who are in the single family world, in the laneway infill house world, it's very tough sometimes to get to the full certification. Much easier to have multi-story unit residential projects or towers, etc. Definitely gets easier in terms of what we have to do in terms of insulation values for our wall assembly in particular. And for example, you know, a single family home in Vancouver could use 6 to 8 inches of exterior insulation. A 4 or 5 story building, that's, you know, a multi-unit residential could use 3 or 4. So it could be that drastic. So keep that in mind. You know, we just got to know that and know that you have to work extra hard if you're working with smaller buildings. And then don't forget about your site restrictions. I mean, a lot of us are designing and working in city environments. There is setbacks, there's fire regulations, and then also what's around your site. Are there any tall buildings, or is there any tall buildings planned maybe across the street on the south side? Vancouver has a lot of trees. It's always, you know, that's a lot of the time, the main thing we factor in is the trees that are lining the streets. And then some of us are in mountainous regions where we have a mountain range that's quite far away, and it can actually impact our solar gains quite a bit as well. So again, promoting design pH, particularly for this stage of your design, where you can add those in. You don't have to get fancy and draw a whole mountain range. What I did recently for a project in Temperate is figured out how far are the tallest mountains away, and all I did was draw a plane in that direction, and that already kind of acts as, you know, the program reads it and realizes, oh, hold on, we don't get any solar gains after a certain time anymore because the sun is behind the mountains. Princess GAIA is asking again, now that we have figured out what range of insulation values we require, how do we choose the right assembly and the right details? I really enjoy or like this. I used some of these slides, probably some of you have taken classes with me, recognize them, and they don't necessarily come from me, they come from my colleagues as well. And I always try to kind of, you know, find an easier way to explain things. And this is one of the slides I really like, especially when we're talking about light timber frame, you know, with non-combustible commercial assemblies. But there's a lot of options always. And again, the advantage of having a performance-based standard is that there is no rules of how we're building our walls, really. As long as we get the U value that we're modeling out of it and put the right values in there, you know, anything really works. So this slide really talks about like wood frame and how can we add more insulation into our assemblies. So there's two major ideas. We either stuff more insulation into our walls, and at some point, you know, we're increasing the depth of those walls. And we'll get more into the details of what that could look like. And the other idea is to start wrapping our existing structure with more insulation with insulation panels. So I picked a few here. There's a lot of variations to this, and don't think again, this is kind of a rule book or what you have to do. It's just showing some of the commonly used assemblies that we, and most of them we have worked with personally, and I can, you know, tell you some of the advantages and disadvantages of these. So in our cool temper climate, so it's very important that we differentiate this. Where do we build this passive house building? Because that will, how much insulation, you know, is kind of the average will differ if it's a cold climate or a cool temper climate or a warm climate. So for us, we are in the cool temper climate in Vancouver, happens to be the same climate as in Central Europe, same as, you know, where Darmstadt, where the Passive House Institute is. So a lot of literature is based on that climate zone. If we're looking at the stuff it category, the easiest one we see in that is a 2x8 or a 2x10 wall that's insulated. And we're getting a, I got it close here, a metric U value of around 0.1 to 0.16 out of that, or a imperial R value of around 36 to 53. So that would be enough here, say, for a single family home. Medium size. One thing you notice here in that little isometric is that something has changed from kind of what we are used to in our buildup of our stud frame wall. We see the plywood or OSB sitting on the inside. And there's a few reasons why we can do that. The main one is really if we're putting it into that position where it's on the warm side of our insulation, it can actually act as our vapor retarder layer. And the structural engineers, they not really care about where you get that strength, that shear strength from, if it's on the outside or the inside. So that means you can get away without using a vapor retarder membrane. So you don't need a, you know, poly, what we used to do, but no Proclima, Intello, or Siga Myrex. You can just use the plywood. And then if you want, you can also make that your primary airtight layer. So now you're adding another function to this material you're already having in your assembly that your structural engineer is asking you to use because the building would fall down like a house of cards if you wouldn't have it. So we making it the vapor control layer, and we can tape it airtight. So now we got everything in one plane. So it happens quite often. So because really it's an economic kind of question of spending more money on material and labor. And now, of course, you know, I'll talk too much about airtightness, but we always want to protect our airtight layers. So we would add in a service cavity to the inside. That's that 2x4 framing you see indicated on this drawing, where we can run our electrical, even plumbing now on exterior walls because it's way on the warm side. So calling this the deep stop wall, sometimes called the fat wall as well. It's one of the most preferred prefabricated panel systems as well. And I saw Jan in the audience there. Hey, Jan, this is, you know, you guys put those panels together for us from Collective Carpentry. And this was actually, you know, quite a large passive house we built in outside of Vancouver, 7,000 square feet. Completely panelized off-site, walls, roof, even intermediate floors. So we used exactly that build-up. We can see the OSB already taped from the factory and then the panels getting installed on site. The one on the right, a little infill house in Vancouver we worked on, that we didn't have set up a crane, not putting any or staging any panels either. So we decided in the end to hand frame it, but still went with that same assembly. One thing to note about this assembly, a lot of time the floors are latchered in, so it's more like a balloon frame than a platform frame, just to kind of make that transition between floors easier in terms of carrying the air tightness through. Now, if we're looking at a cold climate, then we're still in the stuff it category. We need more space than a 2x10. Once you get to 2x12, I think these panels will get way too heavy. So I'll call this the original Canadian high performance wall. And literally, you know, some of you may have heard of Harold Orr and the Saskatchewan Conservation House, which was built in 1970s. And was the first, high efficient house in, I think, maybe North America, which was influential also for Wolfgang and Bo Adamson, who founded the standard. Anyway, they used this assembly there. So I'm pretty sure that this Harold Orr kind of figured this out. He's very humble about, you know, his multiple skills, but the double stub wall. So the idea is that you have one structural 2x4 and then one that's non-structural, and you move them apart as much as you want to get the right amount of insulation you require. So definitely something that's more suitable for a cold climate. Typically the cavity gets filled with dense packed insulation. A little bit trickier to detail all the vapor and airtight layers. I won't get into that too much. Now, rapid is pretty self-explanatory. You're using some form of exterior insulation panels and you wrap them to the outside, or you put them to the outside of your structure. It's like putting on a wool sweater over top of your building. Obviously with that, there's less thermal bridging. We don't have any studs anymore that are thermal bridging every 16 inches. We could do this on top of a regular 2x4 or 2x6 frame. What I'm showing here in the illustration is a CLT panel, mass timber. Could be mass anything. It could be mass concrete, mass block. Definitely one of the most used assemblies for any building that has a bit of insulation, really. And in our experience, this is kind of what we use as our go-to assembly that we do for new construction. And we're using between 6 and 8 inches to the outside. So typically 2 layers of panels that are either 3 or 4 inches. And most of the time you're using mineral wool for this, but you could use wood fiber as well. We'll talk a little bit more about, you know, why would you choose one material over the other. The trick is really to attach the cladding through it. So that's where it gets a little bit difficult. Very easy to do on a CLT. You just, you know, hit the screws wherever. It's mass timber, right? Even the highest density mineral wool or wood fiber will have a bit of flexibility once you tighten those screws in. Those battens will get sucked in. You're gonna get off plane a bit. So it becomes critical that you have some kind of a system in place to straighten out those walls. What we do is just, you know, string line it, plumb the corners, and then work our way up just before we put the cladding on, and just either suck the screw in a bit more or back it off just to straighten it out. If you're going on top of a wood frame, you may have to hit the studs, or you may upgrade your sheathing to 3/4, where it's easier to support some lightweight cladding. If we're looking now at the rapid for a colder climate, I think 2 panels is, in my experience, kind of the most 2 layers it can do. I've seen people, you know, illustrations of 3 or 4. I think you'll get really cumbersome. You need really long screws, and will get not very practical on site. So we have this exterior box that gets added on to our framing. So that could be either made out of a Larsen truss, which is in the top right. It's kind of a cheap handmade truss. A TGI, which is a wood I-joist. That's just off the shelf. They're really designed for floor or roof structures, but you can use them as a thermally broken wood element to build this non-structural box to the outside of our structure. And then it gives you the chance to fill that with insulation again. Bottom right is UMBC, that's a university in Prince George, cold climate, wood innovation campus, a timber frame structure behind this, and they actually used a full truss to build the walls and then insulate in between them. Now, we talked about how a few different methods to get that insulation in. There's a few things we always have to consider, and one of them is our building science. So anything to do with moisture management. So having moisture inside the building, vapor drive, can that dry out to the outside? Very important to not trap any moisture between two vapor type materials. Also, obviously looking at exterior moisture, ambient humidity, rain, snow, wind-driven rain, anything like that. That's what our cladding is for. So we're always talking about the 5 critical layers that we need to have in our assembly. So they will look different depending on how you're building up your wall. And here's just an example. And again, for some of them, there is different approaches. Even in this one, there's a few different ways to get your air tightness on that picture on the right. But always consider that. And if you're having some materials you're not quite sure of, maybe do a hygrothermal model where you figure out, am I gonna have some issues with trapping moisture in this assembly? We just talked about walls for now, but it really is all ties into a bigger picture. You need to have a grand plan for your assemblies. It doesn't make sense to switch from exterior insulated to interior insulated between foundation and walls above grade and then to the roof. So really look at the building more as a whole. And with passivhaus, we typically put a uniform amount of insulation around the building. We don't just favor the attic versus a little under the slab and more on the walls. So it's a bit more uniform. And this is a nice example of where the architect really lines things up. If you're lining things up, it's easier to build and it's going to be cheaper. So it is definitely doable. It doesn't have to be rocket science. Don't forget about the windows. The windows are the most critical piece in your assembly in terms of everything coming together there, your airtight layer, your insulation layer. And just a couple of examples from our job sites. One where we had that exterior TGI, where we had to build a buck to put the window in. And then we're over insulating the frames a little bit. The one on the right is an exterior insulated one where we actually push the windows out into the insulation cavity. So we're using fiberglass angles to support it. And then we're gonna build the insulation around this once it's all waterproof. Don't forget about thermal bridging. So first of all, thermal bridging can occur at any change of direction, at any change of material assemblies. So going through our section and figure out how we're doing in terms of thermal bridging. And if you're using exterior insulation, we really got to pay attention to what is the cladding system, how do we tie that facade back to our wall without creating a thermal bridge. So the old metal set gird that was really like highly conductive, really avoided the insulation value of that exterior insulation. So we have now nice clips made out of fiberglass or stainless steel, thermally broken, or we can use screws and minimize those thermal bridges. Now, Gaia, obviously named after, Mother Earth goddess, is really concerned about Mother Earth as well. And she asked me, how do I minimize the impact on the environment with all these extra materials? First of all, if you have an existing building, consider renovating it, doing a deep energy retrofit. Use the Passivhaus tool Enerfit to certify it. Got some excellent examples out of Brooklyn, all those brownstone buildings. We have a few in Canada, not enough in my opinion yet. One that comes to mind is the Ken Sobel Tower, which is a multi-story concrete building that got exterior insulated. Really, we have to start thinking about our resources. And I was talking to a Swedish, actually a cycling friend of mine, but he was saying, Oh, Sweden is already looking at that they're running out of cement. They don't have concrete forever. They're already starting to look at alternatives to cement. So I never thought of that cement is a resource that actually is going to run out, but we'll face this in our lifetime. So we got to think differently about, you know, what we do with our existing building stock and how can we reuse what we have, keeping the structure, if possible, reusing some materials. So I think that would be the first step really to get into before we even look what the embodied carbon is of materials, which definitely is something I would do looking at new builds, and something that actually is getting implemented already into the Passive House standard. pH ribbon is something that some of you may heard of. It's a tool to look at what is the embodied carbon. And for some of you who are not familiar with the term, this illustration really shows it. It's looking at the entire kind of life cycle of a material. It looks at the extraction of the raw material into the processing, manufacturing, transportation, and the use, and then also the recycling stage or the end use of the material. So obviously there's some materials that are just very high intense in energy. When I went to school a long time ago, we just talked about embodied energy. Now we're basically just spinning that with carbon, because energy is, you know, carbon emissions if you use fossil fuels. So the ones who are really bad are the ones who use a lot of energy. And there's spray foam, all the plastics are there, you know, there's made from oil, etc. And then as we're getting into the more natural materials, especially the ones that are grown, they actually sequester carbon. That means a plant absorbs CO2 during its growth. And if we don't burn it and releasing that carbon again, we're locking that carbon into that material. So using wood, the most typical naturally grown material we work with, actually is a really good thing to use that for construction in terms of low embodied carbon, using mass timber and using light wood frame, using wood insulation, wood fiber insulation, and obviously cellulose, a byproduct of that too, or cork, wool, hempcrete, all these different things we see. So definitely something I would consider. You know, it's always a question of can you get the material and how expensive it is as well. And talking about expense, GAIA says, that sounds all good, but my father has a budget. How much will this all cost? I always like to explain it this way. It's an economic model really to explain why high performance buildings make sense in a very easy way. And the model is called the cost of monthly ownership. So basically you're figuring out what is your premium to go to high performance, to Passive House. And then you figure out the additional mortgage payments you're gonna have to pay per month. So you let the bank carry that additional. And then you subtract the savings you're having from your energy bill. And then if you're basically even negative under the bottom line, it's a no-brainer, you're saving money every month, right? So who wouldn't want to save $135 each month? Let the bank carry that extra premium to go high performance, and you're having the savings. Now, this is a project of ours where we incorporated photovoltaic. So they're even generating, and you see there's energy production. So there's even a bit more, but obviously that costs quite a bit of money too. So even with that kind of scenario, it starts making sense for these clients, homeowners, building owners to use the high performance standard and, you know, saving for the lifespan of the building. The next thing I like this Pempina Institute or list here. They figured out how much does it cost to save a kilowatt hour or to produce a kilowatt hour. And you know, you buy it from BC Hydro, whatever, from your utility. That's one cost. Or you can buy all this equipment and put it on your building, and you figure out how much did that cost and how much is the yield, and then you get a kilowatt hour cost as well. The cheapest way to buy energy is actually to conserve it. So to buy insulation, to buy good windows, to buy an HRV, to buy membranes for air tightness. You start with that, and you're much cheaper than anything else that you can buy, any kilowatt hour you can buy on the market. So this is another good way I find to really make an economic point for high performance building standards like Passive House. I did a presentation a few years ago, and we looked at a few different buildings. This was with a colleague of mine, Lucio Picciano, and we were in Munich at the International Passive House Conference, and we looked at a few of our buildings, and we looked at the spread kind of between where we're spending money on Passive House features like windows, insulation tapes, and the HRV, and we compared it to a regular building. This is just a little snippet out of it. I really want to just draw your attention to how big that pie is, the pale blue, which is interior and exterior finishes. We have a lot of control over that part of the pie, right? We don't have as much when we're doing a Passive House over, you know, the structure, the insulation, the windows, the HRV. But we can save a lot in using more maybe off-the-shelf, not too super expensive interior and exterior finishes. So this is a concept we do in our residential, you know, single-family building a lot. The owners get it and go, okay, I don't need this expensive tile from Italy. I can do something else, or it's just being smart about their choices. So both Princess GAIA and King Cole were convinced. They hired the squire. By the way, his name was Wolfgang, of course, to conduct an interfit on the castle. And after the completion, there was a big party to celebrate the Passive House certification and the royal wedding. And GAIA and Wolfgang lived happily ever after in their energy efficient castle, full of summer comfort to the end of their life. And that's it with the official presentation. I hope you enjoyed it.